So I'm going to be talking about some experiments that I've been I've been investigating the topic of compiled time signal chains over the summer, and I would like to show what I've found so far. A little bit about me: I'm a developer at Ableton, where I work in the sound team, and I've been based in Berlin for about 5 years now. Now this talk's going to be in roughly 3 parts, and I'll start with motivation, why do I care about this topic? Where this started for me was in February, went to the C++ meetup where André Bergner presented his flows library, which he presented yesterday. And I found this a really exciting library, a fascinating way of declaring DSP. It's an embedded domain-specific language, for those of you who don't know, inspired by Faust. And this is what it looks like. It's using Boost Proto to enable a very terse syntax for declaring signal chains. In this case, it's declaring a bichord filter. And the machine code that this generates is extremely optimized. It's equivalent to if you were writing the code by hand. That's the idea. And I found this extremely interesting and wanted to explore some of these ideas. And see what I could learn from how this kind of stuff works. I find it very interesting. It's inspired by Faust. Faust is a DSL, so for declaring DSP in the same way, a very terse syntax. And then you can, from the abstract, the high-level representation of the algorithm, you can generate other representations, like you can generate a graphical representation of the code, or can I get the pointer here? Is that going to work? Yeah. Or here, this Faust code has been converted to C++ code in this case. And something else that I find very interesting about Faust is that it's based on work that's gone into a basic algebra for signal chains. So this idea of flonomials, I think they're called. And so to give you an idea of what this is, if you're not familiar, you get these basic ways of connecting nodes in a signal graph. In this case, a serial connection, A goes into B, and then we get a result from B. Or parallel connections, where you have nodes which are operated in parallel, operated on in parallel. You can merge signal chains, so you can reduce 2 chains into one, or vice versa. You can go the other way. And also you can declare recursive structures. So if you want to introduce feedback into a system, which is very important for DSP, then you can do this with the tilde operator. And I think this is fascinating. There are a few more building blocks, I think, but to give the idea that these basic components can be used to declare arbitrarily complex signal chains, I think is very cool. So I find this all worth exploring. And what I wanted to figure out was if we could apply the same kind of ideas to a higher level of abstraction. So this is very low level to me. This is the almost like electrical engineering kind of declaring circuit level DSP. And the level of abstraction that I'm more interested in myself is this kind of level of abstraction. This is Reactor, where you have a collection of ready-made building blocks like filters and oscillators and all sorts of useful components, which you can then wire together to build instruments and effects in a very high-level way. And then you get parameters that you can tweak really easily. And this is awesome. And something that I like about this level of abstraction is when I'm working in Reactor or Maximus P, I'm kind of in more of a creative flow. So I'm kind of using my creative brain more than my engineering brain. So I like working at this level of abstraction for prototyping. And I think the key thing here is expressivity. It's very easy to declare the high level of what it is that you want to build. And I think although graphical languages have their problems, there are issues with working with these kinds of languages, I think there's something very charming in how expressive you can be with them. What I find is usually missing from Max or React is performance. So if, as a C++ developer, I want to be building algorithms that are extremely performant, if we're going to be shipping like DSP, then it should be running as fast as possible. And usually for us, that means hand coding the algorithms in C++. And this can take quite a bit of time. And so it's a bit of a drag when we've had this like really nice creative flow where we're prototyping ideas and like user testing, and we're excited about what we're building, and then we break down the production tasks, and it's going to be 6 months of work to get this thing out the door. And this is something that I'd like to avoid. I'd summarize this as reducing the gap between prototyping and production. And I think there's a lot of value in this. We can iterate faster, we can try out more ideas. Like we're able to explore more and in the end build a better product the more we can move quickly when generating ideas. And I think there's a couple of approaches to this, to reducing this gap. One would be making your prototyping language better at delivering production code. And Faust would be an example of this. If you could take Faust and prototype your DSP quickly there and then just hit build me some C++ code, and then this code was as efficient as possible, then this would be a good example. Another example would be Gen inside Max. It's a sub-language where you can declare low-level DSP algorithms and export C code. And people use this for production, but for us, the performance isn't quite there, and we would like to be able to go further with how quickly the code runs. Another approach is to make your production language better at messing around with ideas, and that's kind of what I have become interested in. Like, how can we make it as easy to make a synth in C++ as it is in React or Max? Now, expressivity, which is what I'm looking for, often implies flexibility, and flexibility in C++ languages often means dynamic polymorphism. So you'd have a collection of virtual nodes with virtual process functions. Then you have a graph based on vectors where you push a bunch of nodes into your graph and you wire up connections, and this is, like, it works, but there are issues with dynamic polymorphism. The issue for me isn't really about the virtual function calls. There's a jump that the compiler has to make here, or the machine has to make to get to the actual object. But with modern CPUs and branch prediction, like, this is highly optimized, and it's not the big problem that it maybe used to be. But there are other issues at play here, like when you have all of these nude objects being stored in your containers, they're being nude potentially in arbitrary locations in memory, which means that maybe your runtime state isn't very cache friendly. And also a big issue is that the code paths, so the code between modules, let's say, they're segregated behind these virtual function calls, so the compiler isn't able to see through the signal chain and perform any kinds of optimizations that it might be able to make if you had like a few gains in series or something. But you probably wouldn't do this, but if you did, you'd be able to collapse some of the calculations, perhaps. Now, with the arbitrary memory issue, I would say that you can get around this. Like, if you store all of your objects in the right way so that they're cache friendly, or if you use an arena allocator or something, you can like avoid the issues of cache friendliness. But this is the kind of engineering work that increases the gap between prototyping and production, and that's basically what I'm trying to avoid. Yeah. So something to say is that most of the time we don't actually need this runtime flexibility. Since most of the time we'll have a fairly fixed architecture. Like, you might have a switchable filter or something, but really the overall architecture is fixed. It's only if you're building like a modular synth that you need this kind of dynamic flexibility. So the question that I was asking myself is, if we know the signal chain at compile time, how can we tell the compiler about it so that the compiler can optimize as much as it can? Like, is there value in doing that? Like, what will the compiler actually do if you are able to provide it this information? Now, one way of doing this is that you code your structures by hand. So you create a voice class, and inside there you have a filter class and an oscillator, and you tick the oscillator and you run the result into the filter, and you do this manually in the code. And this works. Like, the compiler will see through all of this and optimize it as much as it can. But again, like, to me, this is engineering, and like lots of boilerplate in C++ where you declare your classes and have to wire everything up together. And it's not such a pain, but it's also not Maximus P or Reactor to me. It's C++. So I really wish for a library that allows for maximally expressive signal chain declaration while allowing the compiler to produce maximally performant production-ready code. And so that's where I got to with my thinking and why I started exploring this. And how have I got on? Well, I haven't succeeded yet. I'd say it's very incomplete what I have. What I'm showing is experimental. I don't have a ready-to-use library at the end of this that I would recommend that you use. It's all experimental, but hopefully it's interesting. And that's setting the scene, I think, for part 2, which is baby steps. So what I did was I started by sketching out some very simple examples. I was really trying to think, like, what code would I like to write to be able to, like, build my synth, let's say. So I started off with some basic examples, like, let's declare a serial chain of some nodes. We have a multiply node, an add node, and another multiply. And then we can assert that if we send a value in to the chain, then the correct result comes out. Then the same thing for a parallel structure, like send a 10 in and we expect it to have 5 added to it and 42 and multiplied by 2, and then sum those node results together. So I think this looks okay as a starting point. Let's look now a little bit at how this works, so we can understand what's going on. The first thing I'll show is how we declare the chains. So we have these functions, serial and parallel, which return serial and parallel structures. Now, something to say here is that these are using variadic templates, and maybe not everyone here is familiar with them, so I'll like explain a bit. What you have here is like a template. I'm assuming we at least are familiar with the basics of templates, but if anyone's got a question, please just jump in. So we can throw into these functions an arbitrary number of nodes, and the nodes can all have different types. So you could have a filter or an oscillator or anything, and these T's here are like capturing those types. And at compile time, the compiler will swap in the necessary information, right, behind those dots. Like, you have an arbitrary number of types. And then in the function call, the parameter, this is like a runtime, you have an arbitrary number of values of arbitrary types. Now, a bit more about how variadic templates work. This is like just an example. We have a main function that prints out an integer, a double, and a string. And at runtime, we're going to go into this function first, and what the compiler will do is peel off the first element, put it in T, or like it will have type T, and the element will represent that value, and then it puts the rest of the values into like this T's rest value. Does that make sense? Like, so I'm not maybe explaining it brilliantly, but then it prints out that element that it's captured, and then prints out the rest. So it recursively calls this function with all of the types that are in the list, the values that are in the list, and then eventually, when there are none left, signature, because there is no single T, we're at the end, the list is empty, and so it falls back to this implementation of print elements, and it does nothing. So that's like the terminating case. So does that make sense? Cool. So now that we're comfortable with that, we should be able to understand what's going on here. Now this is the serial change struct, where we have, first of all, a single T and then a bunch of other Ts. And that single T represents a node in the chain. So we have like the first node, then it's captured, it's stored here, and then we inherit from serial again, but with the rest of the Ts. And so then this creates like an inheritance hierarchy where each level captures one node, and then the rest of the nodes are captured in the base classes. Then if we call process on this node, we pass the input into the node's process method, and then take the result of that and pass that into the base class's process method. Does that make sense? Cool. So then what's missing here is the terminating case, and that's shown here, where we have an empty list of T's. Like, we know it's empty because if there was anything in there, this one would be the capturing signature. So this is empty, and then the job of processing the input is to simply return it. It's like that's the terminating case, that's the result, that's what gets returned, and there's no more work to do. Cool. And then the parallel version of this is very similar. It's the same pattern, but now instead of passing the result of the process function for your node, you're not passing that into the next level, you're summing it with the result of the next level. So this recursively like adds the result of the node to a result. Then for the terminating case, we oh, sorry.
More nerd than parallel, then you would just sum the results.
Yeah. Yeah.
Why do you need a tuple if you want the real parallel composition? So you have to have multiple outputs.
Yeah.
Do you do that?
Yeah, I explore. Sorry, the question was why haven't I called this merge instead of parallel? And yeah, the behavior is more merge than parallel. That's right. The reason that I took this approach is that for the most part, I'm more interested in trees than like arbitrary graphs. So at this level of abstraction, I found that it's easier to declare a parallel chain if the default behavior is that it sums. I'll show you later an example of when you don't sum. Yeah. But maybe the name isn't the best name. Yeah. Then I can show you the modules, the nodes, sorry. Like here's add. This is simply a struct with an amount, and then whatever comes in has amount added to it. And then a little helper function to declare it in a simpler way. And there's multiply, it's the same deal, but a different operator. And then if we put all of that together, we can create a fairly complicated tree of adding and multiplying with parallel and serial branches. So here we have two serial branches which are being summed in parallel, processed in parallel but then summed. So if we pass 2 as input, we end up with the correct result, let's say. So I can show how this works. I can show what the compiler does with this by using, oh, shite. I forgot to sign up to the Wi-Fi. Give me a second. Is that going to work? Oh, well, that's a bummer. Yeah, and but I'm not getting a pop-up. Oh, no worries. Yeah, it's all good. Yeah, so I could actually do with internet. That's going to be a bummer if I don't.
Maybe. So you're on guest and it's not popping up.
Any chance you got an Edgy Room login?
I can try mine.
Yeah.
use my laptop if you have the link.
Yeah, maybe. I'd need to download the talk.
Oh, right, okay.
Yeah.
Maybe we can go through. No, we can't. To change that.
Do you have Chrome? I don't know if it might be the browser.
Oh, have you got your pop-ups enabled? Maybe that's it. Why it's not popping up?
Yeah, I don't.
That's the long version. That should work.
Hey, that's looking good.
Sweet.
Hey, thank you.
No worries.
Nice one. Right. Sorry about that. I forgot that I needed to sign up. Okay, so here's the example that I just showed you, where we have. Sorry, is that visible? Maybe I'll make it bigger. Can you read that at the back? Is that all right? Yeah. So, what this website does is it takes C++ code and then it spits out the machine code that is generated by the compiler when it's compiled your code. And you can choose versions, which is really awesome, and no Visual Studio, sadly, but maybe one day. And this is great. Like you can, it color codes like your expressions, and then the machine code that relates to the expression that you've expressed in C++. And you can make changes, and then it automatically compiles. It's just like hot compiling your changes all the time. Now, what we see here is that there's like quite a disappointing amount of machine code being generated for this expression, this main function. But if we enable optimizations, then it's able to completely see through the whole structure and give you the correct result. So the answer is -14, and it just returns that. It skips the assertion because it knows it's true and just returns -14. Now, that's a bit unrealistic because it's a constant input, but if we change it to be a random number, then we get a bit more. Most of this is about the assertion because we can't predict that the assertion is going to be true. But if we remove the assertion, then this is like the minimal calculation that the program has to do to deliver the correct result. And I think this is pretty remarkable. I'm very excited about this, that the compiler is able to see like through all of these structures and like reduce calculations where possible. Like it's not doing literally the calculations that I asked it to do. It's reducing it and doing what it can to simplify things.
Can you use a static assert there? Set that out of the equation?
You could do a static assertion.
I mean, it's all templates, right? So,
Well,
that would just compile time as well.
yes, so a static assertion, sorry, the question was, could this be a static assertion? It could be a static assertion, I think. You could express that the result should be, no, this would require some runtime, so this is a runtime function. I could make it const expert, and then I could,
That's what I'm thinking, context.
yeah, I haven't done const expert, added const expert support to this library, but you could start thinking about that, right? And then this could be a static assertion, that's right. Yep, sorry. Yeah. I mean, yes. So, sorry, the question is, if these were floats, then would the compiler be able to do as much in terms of optimization? With fast math enabled, it can, I would say. Like, there's an example of this that I'll show later. But yeah, if you don't have fast math enabled, then it can't guarantee correctness of the resulting values. But if you do fast math, then it's a lot more aggressive with the optimization. Yeah. Okay, so let's go back to the talk, the slides, let's say. I wanted to check that my assumption held that dynamic polymorphism for a simple example like this isn't as optimizable. And so I put together a little serial chain, a parallel chain, and like a virtual interface for a processing node, and then store nude objects into vectors, and then wanted to see what the compiler can do with that. And even with like O3, there's tons of code here. Now, like you might say, yeah, but does this really matter at runtime? And maybe I should do benchmarks or something. And I would say, yes, I should, but I haven't. But let's just say the thing that I'm interested in really is like, what can the compiler do with the information that you provide it? And I hope this shows that there is value to like thinking about like static polymorphism and like using the type system to let the compiler do as much as it can, if that makes sense. So far so good, I would say. I'm quite happy with how this is going. But a big issue for me is that this is all static. There's no interactive runtime behavior here. So I wanted to start thinking about how could I add exposed parameters, like if you want to tweak filter cutoff or something with a MIDI control, like how would we be able to express that and let the compile chains like support that. So that's what I started to explore next, which is leading me into part 3, where I type all the things. And I started off with like what I would call a fairly traditional approach of declaring parameters for a processing module. Like I started with this kind of module and processor split, which you'll often see in synth libraries. And an enum of parameters with like a parameters getter, which where you can declare a bunch of parameters. You say, I have an amount parameter, and there are some properties attached to it. And I started thinking about how you might access this information in the DSP code, and there's a parameter getter where you say, give me the parameter that matches the enum value. And I mean, I wasn't very happy with this, and then when I started exposing this at the signal chain level, I started like having to have runtime IDs for my modules, and this all felt wrong. I wasn't really speaking the compiler's language somehow. So I wanted to find a way to express this stuff rather than using runtime getters and enums. I wanted to find something that was a bit more like type system based, let's say. And here's how a processor host looks, and we have set parameter, and we have an ID and an index, and we scan through the processors and look for the correct index, and I wasn't satisfied about this direction. One thing to say here is that I've started using Boost HANA, which is a really awesome library. If you haven't seen it already, it came in a couple of versions ago in Boost. It's a C++ 14 only metaprogramming library, and it's a work of genius, I think. It's really incredible, and if you've been burned by metaprogramming languages in Boost before with like long compile times, the compile times with HANA are like in some cases orders of magnitude faster, thanks to use of C++ 14 features which enable metaprogramming techniques which the compiler can just chew through much faster than the old ways of doing things. So the thing that gave me the breakthrough to a better approach, I think, for parameters was speaking to an ex-colleague over a beer, and he asked the question, why can't the parameters be types? And this was like a light bulb going on for me. It was a big jump forward. If we really express the parameters as types, then that allows the compiler to do a lot more. So that's what I started working on. And this is pretty much up to date with where I'm at now. I have a parallel structure with 2 gain modules. And I say a module of gain type, which has a value of gain amount type. with a value of 0.5, and then another one with 2, and then if I create a processor for this chain, then I can tick it and get the correct result out. And if I want to expose parameters rather than just setting them when I construct the chain, I can tag the parameter that I'm interested in an expose wrapper. Like this is basically just tagging the type and saying I'm interested in this parameter. And then when I create the processor, I can ask for the processor's exposed inputs and then access them by index. So this gives me a flat list of the exposed parameters, and then I'd be able to, in theory, like hook up a UI to this or MIDI controls to these parameters, so I can set the value at runtime. Yeah.
Sorry, you've got a value gain amount as your gain type.
Yep.
Does that have to be named? Can you just not use an unnamed template type?
Oh, sorry. The question is, why do I have to specify the type of the value here?
Yeah.
Well, my thinking was that if there's a more complicated module, like maybe an ADSR envelope with multiple parameters, like attack, decay, sustain, release, etc., then you would want to be precise about which values you're setting. I mean, if it was just raw numbers in a list, then you would have to know what order they're supposed to be in. But this way, they're kind of annotated, so they're human readable, and they're correct. So the compiler knows exactly which value this has to go to. And you can put them in any order, and I'll show later, there are also assertions in place to stop you from using the wrong kind of parameters. Let's see now. So a gain module looks like this, where we have a namespace called gain, and inside the namespace we declare an amount struct which has properties. So this amount is a parameter that we're then exposing in the module struct. So there's a convention of saying module parameters is a type def or a type alias for of parameter traits, and this could be any number of parameters. So this could be n parameters in a list. Then the processor has a constructor where the inputs are passed in, and we store the inputs, and we'll come to why we do that later. And then we have a tick function. So this is the same thing as process or calc or any other name, and we get the value for the amount type from the inputs structure. So I find this fairly straightforward in terms of the code that you have to write to get the value, and this to me is like the minimal processor that I could come up with. I was trying to reduce boilerplate as much as possible, and this is what I have so far. Then at the end you say gain is the gain module. So this allows me to refer to this module as gain in the the main namespace. Parameter traits is just a type alias for stud tuple. So it's a variadic type alias, which is just a convenience, because if I didn't do that, you would have to say here parameters equals stud tuple amount, and then maybe that's confusing. So I figured a type alias makes it hopefully more usable. Now, how do we declare a module? You declare it like this, and this is a lot of code, so let's break it down and go through it line by line. I think this is quite useful to understand, and so hopefully it's understandable if we just step through it. So we have a constructor which takes a module name, but there's also an overload which doesn't take a module name, which dispatches to this one. Then a collection of values, so n values which you want to set for the parameters. Then there's also a template parameter, which is the exposed parameter list. Expose is just a simple struct which takes n types attached to it, let's say, which allows me to access the types that you specify. But it's just a way of tagging those types, bundling them together. Now the next thing to do is to get the module's parameters. So you could have a module that doesn't have any parameters, maybe a DC blocker, or like if you just have a debugging module which wants to trace out the values that come into it, you don't need any parameters. So as a usability feature, I figured it would be nice to make it optional. And so then we get the module parameters from this helper module parameters, which looks up in the module struct for a parameters type, and if it isn't there, then it defaults to an empty list of parameters. And that works through template partial specialization. And if you haven't seen this before, what this is doing is it's saying we take module traits as a template parameter, but we also put this placeholder in here, which you don't have to specify as the client, but you can think of this void as a placeholder for specialization. So in the default case, we just have an empty list of parameter traits. But if the module has declared some parameters, we should use them. And this is a template specialization where we have our module traits, and then we say we access the module traits parameters and then cast it to void so the signature matches. This is just a thing you have to do in C++. And the compiler looks at this for a module, and if it has parameters, then it considers this specialization to be more specialized for that type, and so then it uses this specialization. So hopefully that makes sense. If you haven't seen this before, it's really like just a way of switching and saying either we use this one or we use that other one. Then, after we've got the parameters, we have a static assertion which checks to see if the values that you've specified actually reflect parameters which are in the module. And this is important because if you, with your filter, specified a value for gain amount, then this would just fail silently. Nothing would happen. The value wouldn't be applied. And you'd have to dig into figuring out why. But the static assertion blocks you at compile time from making a mistake. I can show you the implementation. I think I'll skip over this because we don't have so much time. But just to say that I figured this took a while to figure out, and I felt that it was worth it just from the point of view of usability. If you want an expressive library, then it should stop you from making mistakes. So this doesn't actually add anything to the library. It adds to the user experience, if that makes sense. Then the thing that we want to do is create a list of parameters derived from the module's parameter traits. And if the user has specified any default values for these parameters, then it needs to apply them. So for each parameter, we create a parameter with the parameter traits, and then we pass in the value list, and if there's a matching value in the value list, then it applies that instead of taking the default value. Then given that, we create a module host which is typed on the parameter list, and also we pass in the exposed parameters. So hopefully that makes a bit of sense, some sense at least. But this is like a standard utility for creating modules. So this is like the details of how it works, and hopefully it's interesting. Then when we create a module host, we have our traits parameters and the list of exposed types. And we store our exposed parameters. You don't have to care about why. But something, again, that's interesting here, I think, is the static assertion that I add that checks that the exposed parameters are actually in the parameter list. And again, this is an important feature. If you try and expose filter frequency when you want phaser frequency, then that's an easy mistake to make. It's a mistake I made, and then you end up with horrific, horrible template error messages. And so the static assertion helps with that. I'll show that in a second. Yeah, so here's an example. We have bichord, and I've expressed that I want to expose phaser frequency when I meant bichord frequency. And you get a template error message which is deep in Boost HANA code, and this stuff goes on for pages and pages. But with the static assertion, then you get a human readable error message at exactly the correct location where the failure occurs. And then the next note is saying where I made the mistake. Well, actually, no, that's not true. It would be the note afterwards. But so to me, this is just a usability feature. Now, when we create the processor for a module host, we want to create a collection of inputs for the processor that reflect whether or not the parameters have been exposed. Now, this is useful because if the parameter hasn't been exposed, then it means it will never change. So we can choose to either express the input as a variable input with a value setter, or we can say it should be a constant and it will never change. That allows the compiler to optimize away possibly varying values. So if you have something like a filter and you set the properties of the filter such that it's a high pass filter and you always want it to be a high pass filter, then you can use the same filter and all of the parameters get composed as constants. And it means that you have a filter that you can either use as a runtime filter or a compile time constant filter, or a mix of the two. So maybe you have a shape switch for an oscillator, and maybe there's an if somewhere in your code. If that's a constant, the if will disappear. Now, how does that work? Well, maybe I'll skip over this quite quickly because I'm kind of running out of time. But what I would say is, well, that's quite complicated. But let's step through it. We're making an input map based on the list of parameters. And using Boost HANA, we can have a map which is based on types rather than on values. And the key to the map is the parameter traits that we're interested in. So this would be gain amount or filter frequency. And that's important so that in your DSP code, you just have to say get value amount, and this will look up in the map for the input which is assigned to that value. And if it's a constant, this will resolve as a constant, but if it's a variable input, then you'll get the latest value from the input. Then to create the value of the input, first of all, we get the parameter from our parameters list. And then we call make input on the parameter. And we pass in. Now, this expression looks quite hairy. But really it's saying, is the type in the pack? So the pack meaning the list of types. So the parameter pack. So if this traits object is in the exposed list, then it resolves as true. So then make input is being called with either true or false. And then we do this for every parameter in the list. Make input then inside the parameter object has an input selector. And we pass in this Boolean, whether or not the parameter is exposed, into the input selector, and then we get the resulting type, and we assign the default value to the created input. And the input selector is, well, in my code, more complicated than this, but because I've added another type of input, which I'm not going to get into, but if you're interested, we can talk about it afterwards. But really, it's just at this point saying, if the exposed Boolean is true, then we take the input type that I showed you earlier, or the constant type that I showed you earlier. So that's good. Like we've managed to create processors with inputs which are variable or constant. Then how do we expose them to the user? Well, I'm going to start at the processor level and then work back up to the user level. And here we have a processor host. Now, this thing contains a processor, which is the modules processor that you've declared. And Yeah, so this is hosted up at the top, and then there's a tick function down at the bottom, which just calls tick. Exposed inputs is the interesting thing here. And what we're doing is we're returning a tuple, a list of types, a list of values. The values are pointers to the exposed inputs. And so it's looking up in the processor's inputs map here for all of the inputs which are in the exposed list. I mean, I don't expect you to necessarily understand this, but the behavior is that it's like at runtime accessing a pointer to the variable input and then returning a list of these pointers. And then for a processor group, so this could be like a serial group or a parallel group, we're taking the list of exposed inputs from each processor. This is the transform. We take the list of processors, we get all of the processors' exposed inputs, and then we flatten these tuples into a flat tuple. So instead of tuple of tuples, we get one tuple which contains all of the exposed processors. And then this like happens recursively all the way up to the top of the tree, and you end up with a flat list. So now at the user level, I can show you how this looks. So we've declared like two modules in series. We have a phaser and then a gain after the phaser. Here's a feature I haven't showed you yet where I can declare a module and then reuse it and assign a name to it. So I've declared a phaser and then put two of them in parallel with different names. Then I can ask my chain what the exposed parameters are. The exposed parameters being like the module representation of the parameters rather than the runtime processor. Sorry, I mean, that's not entirely correct. These are being accessed at runtime, but the module processor separation is coming into play here because in my DSP code, I don't care about things like names of parameters. So my DSP structure doesn't have any name stuff in it. It only has DSP stuff in it. So you can ask for the exposed names, which is maybe useful if you're building a UI. Then when you create the processor, you can ask for the exposed inputs and then set a value on the input. Okay, cool. So that means that we now have like things that I could at this point attach a MIDI control to this, so I'm pretty happy about that. Then I wanted to look at some different kinds of structures, and like I've got a recursive structure, so this is like a forward chain and a backwards chain. So this first one is the forwards chain, and then in the feedback loop you have another gain, which is reducing the signal. So when you feed an impulse in, first of all we get 2 and then it decays. Then also, here's the example of split, which is parallel but doesn't do the summing at the end. And then that means that you can have 2 chains which are then fed into a crossfader. The crossfader receives an array of values which are the results of these chains. So where is this going? I mean, that's about all that I have. In the end, what I'm imagining is that you'd be able to create a full synth out of this. Now, some of this stuff I haven't implemented yet, but like this is what I would expect it to look like, maybe, where we have an oscillator, and then we have an oscillator section, which is 3 of these oscillators being summed together. Then we have a filter section, which is 2 filters. Maybe this should have a mixer or a crossfader on the end of it, and an envelope, and then for a synth voice, we can declare that we have the oscillator section running into the filter section, running into an amplitude envelope. And then this would go on to say like a polyphonic collection of voices running into an effect section or something like this. And you know, so I kind of like this. I think this is quite expressive and like you can quickly put things together. So I'm quite happy about that. We could think about maybe a less verbose syntax for this, maybe using operator overloading. Like we could have the pipe operator for serial and some other operator for parallel. But just in terms of expressivity, I think for C++ this isn't too bad. So what would I like to work on in the future on this? I think some useful DSP building blocks would mean that I could actually start making some proper audio stuff with this, like oscillators and filters and things. a modulation system would be like really nice to have. I haven't quite figured out how this should work, but like if you have any ideas, then I'd be really happy to talk about it. I need to add polyphony. I'd like to experiment with a different syntax. And I think it would be really nice to show the value of this way of working if I could automatically generate a UI. This would be quite nice. So to go back to what we were looking at earlier with what the compiler can do with these kinds of structures, now that I've added a lot more stuff to the framework, I wanted to revisit, like, is the compiler still able to optimize this stuff properly? And so to try this out, I set up a little recursive structure, and then we feed one into it. This is operating on doubles, just to go back to the earlier question. And we get the result. It decays down to 0.125, and then because we have a main function that returns an integer, we multiply it by 1,000 so that we get a result of 125. And then I can't use Godbolt with this because Godbolt doesn't have boost, so that's a shame, but I can show you the IR, the LLVM IR, which is generated for this, and it's really still able to like see through the whole structure, not just the structure, but the ticking of the structure of the processor to the point where it just knows that the answer is 125. And yeah, this requires fast math to work correctly. If you don't have fast math, it has to do a bunch more, but you know, for DSP stuff, maybe you're enabling fast math, so it's okay. And another example where we have a random input. So instead of constant, we don't know what the answer will be at the end. But the compiler is able to tell that whatever the random input is, the answer will be random times by 125. And I showed this last week to a colleague of mine, and he said this was creepy, which I thought was a great word for this. I think it's because of the feedback. The fact that the compiler is optimizing the feedback away, this is the creepy bit, I think. But I think it's awesome. I think it's remarkable what compilers are able to do here. This is mind-blowing to me, and makes me excited about like taking advantage of what the compiler is able to do. So I think the conclusions I have from this are help the compiler to help you. It wants to optimize your code, so give it as much information as you can, and it will do what it can. Like if you hide information, then what can it do? If you're like experimenting with template metaprogramming, template-based libraries, then I'd really encourage you to help your users try and figure out what kinds of mistakes they'll make, and then put in assertions wherever possible to like make life easier for them. And in general, I would say that template metaprogramming is something that I haven't really investigated before. I started with this project basically, and it's much easier now in C++ 14. So I'd encourage you to take a look. So thank you for your time, and I'd be happy to take questions.